Hi, welcome back. In our last lecture, we discussed the equation obtained by applying Stirling's approximation. That is the equation for probability W. That is ln W is equal to n ln n plus sigma ni ln gi minus sigma ni ln n. This is our equation for thermodynamic probability W. And we discussed that at a maximum value, the derivative of a function becomes 0. At a maximum value, the derivative of a function vanishes. So, when we differentiate this becomes 0. Because the maximum value of probability is 1, or maximum value of a function is always constant. Maximum value is constant, so when we derive or we take the derivative of that, it becomes 0. So this term becomes 0. Right? So we can differentiate all terms plus the differential of which is equal to 0, because probability, maximum probability is 1, so its differential is 0, or its log itself is 0, so we can say which is equal to 0. Then n is the maximum number of particles or total number of particles. Total number of particles is also a constant value. It will never change. So the differential of total number of particles also 0. That means this term also vanishes. Then the remaining term is df ni ln gi minus differential of ni ln ni, which is equal to 0. And we can differentiate both terms using UV rule. So keeping ni constant and differentiating ln gi, we get sigma ni d ln gi plus keeping ln gi constant and the differential of ni, that is d ni, minus the same thing here, sigma ni d ln ni minus sigma ln ni d ni is equal to 0. Keeping ni constant, differentiating this. Okay, the same thing. Then differential of ln gi, we know degeneracy of an energy level is constant. It is same always. So differential of ln gi 0. That means this term becomes 0. That means this term vanishes. So the remaining terms, so this term will vanish, and the remaining term, it is sigma ln gi d ni minus sigma ni differential of ln ni log ni differential of log x, which is equal to 1 by x dx. We know it. Differential of log x is 1 by x dx. So differential of log I ni is 1 by ni dni. So this term can be written as 1 by ni dni because d ln x is equal to 1 by x dx. So d ln I is equal to 1 by ni dni minus sigma ln ni dni is equal to 0. We can cancel these terms. So the equation becomes sigma ln gi dni minus sigma dni minus sigma ln ni dni is equal to 0. The sigma dni, we know sigma ni which is equal to total number of particles. Sum of the number of particles equal to total number of particles. When we differentiate it, that is sigma dni, which is actually equal to dn, which is equal to 0. That means sigma dni is equal to 0. So this term vanished. Okay, so this term becomes 0. Then we can write the equation as log ln gi dni minus ln ni dni is equal to 0. dni common terms. Then if we take out the common term, the equation becomes ln gi minus ln ni, log a minus log b. So we can write it as log a by b. So the equation becomes sigma ln gi divided by ni dni is equal to 0. It is our equation number 1. Okay. Then we have to solve the equation and find out the distribution of Ni particles in Ei energy levels with Gi degeneracy. So the distribution of Ni particles in Ei energy levels with Gi degeneracy, Gi multiplicity. So in order to solve this equation, we are using a method called Lagrange's undetermined multipliers. That is the method we are using. Okay. And for this, we are taking the equation that is dni is equal to 0. Okay, that's our equation number 2. Then total energy. Total energy is the sum of the energies of all levels. Suppose n0 particles occupied in E0. So the energy of the level E0 is n0 into E0. And energy of the first level is n1 E1. And the energy of the total energy, we can say it is the sum of the all energies. That means sigma ni Ei is the total energy. Right? The energy of E0 level, ground state level, is the energy of that state into multiplied by total number of particles occupied the level. That is n0. n0 into E0. Then n1 into E1, n2 into E2, so and so ni into Ei. So the total energy is the sum of all these energies. So we can write it as sigma ni dni. Then, and we know the total energy of a system is constant. Total energy is constant, so differential of total energy, that is total energy, we can put it as E. If you put it as E, then dE, change in total energy is obviously 0. There is no change in total energy, so it is 0. So we can write that D is equal to sigma EI dNi or D of Ni EI, right? EI dNi. Then this is also is equal to 0. That is, our next equation is sigma EI dNi is equal to 0. That is our equation number 3. Then multiply these two equations by alpha and beta respectively. Multiply the first equation by alpha and second equation by beta, and alpha and beta are called Lagrange's undetermined multipliers. Then we get alpha into sigma dNi is equal to 0, equation number 4. Beta into sigma EI dNi is equal to 0, equation number 5. Add these two equations and subtract it from equation number 1. That is equation number 1 minus 4 plus 5. Then we get, the equation number 1 is sigma ln Gi divided by Ni dNi minus, we are subtracting these two, that is alpha sigma dNi minus beta sigma EI dNi, which is equal to 0. Then dNi, common terms, we can take it out. Then summation, sum over all limbs, we can take it as like this, that is summation to all terms. So ln Gi divided by Ni, we are taking out dNi outside, minus alpha minus beta EI into dNi is equal to 0. And this dNi, it is changing number of particles, number of a specified particle. Maybe N0. N0 is the number of particles occupied in the energy level E0. It may vary. N1 is the number of particles occupied in the energy level E1. It also may vary. But total number of particles never vary. That is sigma Ni never changes. So dNi vary. That means dNi never be 0. So we have to equate the coefficient of this term equal to 0. That is ln Gi divided by Ni minus alpha minus beta EI is equal to 0. Then we get ln Gi by Ni is equal to alpha plus beta EI, or Gi by Ni is equal to e raised to alpha plus beta EI. And Ni, that is Ni particles, distribution of Ni particles in EI energy levels with degeneracy Gi, which is equal to G into G divided by e raised to alpha into e raised to beta EI, or Ni is equal to Gi into e raised to minus alpha into e raised to minus beta EI. This is our desired equation. Equation for Maxwell Boltzmann statistics, Maxwell Boltzmann distribution. Then from this we can write as and this sum over a limit, that is sigma ni becomes sigma gi into e raised to minus alpha into e raised to minus beta ei. Among this, gi is a constant, alpha is another constant, so beta is also constant. So we can sum over only ei, energy, over a limit. So this equation becomes, and sigma ni is nothing but capital N, that is total number of particles, and g is constant, e raised to minus alpha is also constant, so we can put it as sigma e raised to minus beta ei, or can be written as n equal to gi into e raised to minus alpha into e raised to minus beta sigma ei. That is another equation. So suppose we are dividing this equation by this equation, that is n divided by n, which is equal to gi e raised to minus alpha e raised to minus beta ei divided by gi into e raised to minus alpha e raised to minus beta sigma ei. So these two terms cancel each other, then the ratio becomes, that is ni divided by n equal to e raised to minus beta ei divided by e raised to minus sigma beta ei. This is a fraction of particles distributed in energy levels ei. Also another representation of Maxwell Boltzmann statistics. Then we can also, from this we can calculate e raised to minus alpha is equal to ni divided by gi into e raised to minus beta ei. This is the equation for e raised to minus alpha. So we can determine the different ways of distribution of Ni particles in Ei energy levels with degeneracy Gi. So that is the actual probabilistic distribution of particles, and this is our Maxwell Boltzmann distribution. And we can discuss the statistics in details in our next lecture. Thank you for watching.